everybody. I just need to share my screen. Can you all hear me loud and clear?
Yeah.
Yes, Jack.
Okay. And you should be able to see my screen now.
Yes,
Yeah.
we see.
Okay. So yeah, thanks again, Tommaso, and thanks to the ASHRAE Italy Chapter for giving me the opportunity to talk to you all today about liquid cooling and specifically about the challenges in implementing liquid cooling within the data center environments. We'll do a brief rundown of various liquid cooling systems, but what we will primarily be focused on is direct liquid cooling systems or direct to chip liquid cooling systems within this talk, and we'll get into that in a bit more detail. So first of all, just quickly about Kirby and about myself. My name is Jacques Leisegang. I am the engineering manager with Kirby. Kirby is an Irish-based contractor. We're established in 1964, so we've been operating for more than 60 years. We've got a 700 million turnover, and we're working in sectors from primarily data centers, but life sciences and pharmaceuticals, industrial manufacturing, and power and energy. We operate all over Europe, Ireland, UK, and mainland Europe. And we deploy and we employ rather 1,900 people across the group. So that's just a bit about Kirby and about who we are. But yeah, primarily an M&E contractor. So getting into the presentation, the technical part that we're all interested in. So I've broken this presentation up into two main sections. We'll go through an introduction to liquid cooling and what liquid cooling is, and then we'll go through some of the challenges associated with implementing liquid cooled systems within a data center. So why does this matter now? Why is there all this change in approach on the cooling systems within a data hall? So I guess with the increased demand for GPU workloads, this is necessitated through AI, high performance computing applications. Traditional air cooling is not sufficient, and it's struggling to keep up with the cooling demands. I know a lot of us are using these applications, and we can just tell by our everyday use whether we're using these directly, these AI tools directly, the likes of ChatGPT, or maybe we're using them indirectly and we don't even know the websites and the chatbots that we're using do use these AI tools. In terms of high performance computing, that's things like CFD analysis, medical research, and as well as AI training, all plays a part in this increased demand, and this increased compute demands as they rise. There's a need for more effective thermal management. Every time we open the news and we read about the data center cooling and liquid cooling, these rack densities are continuing to rise. You can see there's a snip in there. NVIDIA's Rubin Ultra is expected to be 600 kilowatts per rack. So huge amounts of IT capacity, and as a result, heat rejection needed out of there. The image below there is an extract from some of the 𝗪𝗪𝗔 documentation, and it's a good illustration to show as the rack densities increase, air cooling, perimeter crack or AHU, and raised floor solutions, even row-based cooling with containment, they're reaching their limits. They're no longer a viable solution when you reach up to 75, 100 plus kilowatts per rack, and liquid cooling becomes a requirement. What I will say, and this presentation is focused on liquid cooling, and all the news and the media is all about liquid cooling. It's important to note that not all applications need liquid cooling. There is still a place for air cooling for less demanding and lower density workloads like cloud infrastructure. So there will still be a need for air cooling, but liquid cooling is the one taking the spotlight at the moment. So what is liquid cooling? As the name suggests, liquid cooling uses liquid or a fluid as the primary medium to remove heat from the heat source. This liquid can be a water, it can be a refrigerant or a dielectric. And the reason for this, the reason why liquid is being used is it has a far better, it's a far better conductor of heat than air. Liquids have 3 times greater capacity to capture heat in comparison with air. So that allows a liquid system to remove heat much more efficiently at a much larger volume, and enables us to support equipment with high heat output without the risk of overheating. So there's different types of liquid cooling. Liquid cooling isn't just liquid cooling, and it's the same across the board. There's 3 main ways in which liquid cooling is implemented. Firstly, we have direct chip. You have immersion cooling, and not strictly liquid cooling, but you also have a rear door heat exchanger, which definitely increases the rack density that you're able to manage. So within direct chip liquid cooling, you can either have a single phase or a 2-phase liquid cooling. Within immersion cooling, you can have the you can have the IT chassis within the rack that's submerged in or immersed in a liquid cooled solution as a single phase, and then you can get an open tub or a bath immersion cooling either as a single phase or 2-phase solution. And I guess the single phase is what single phase direct to chip is really what we're focusing on in this talk, and what is expected to be the preferred method of implementation. The other methods are not expected to be predominant in the short term. There will be use cases for it. There will be applications for it that will be used, but the predominant and preferred method of implementation will be the direct chip liquid cooling. So let's quickly, as an introduction, just get into each of those different technologies and what they mean. So firstly, direct chip cooling. So in a direct to chip system, it's a closed loop coolant cooling system. So that utilizes a cold plate. So there's a cold plate which is attached to the CPU or the GPU, and the fluid runs into the cold plates and absorbs and removes heat directly from the cold plates. So around 70 to 80% of the heat generated from the server is removed via the cold plate, but that still leaves about 20 or 30% of heat generated from things like the RAM, the disk storage, that will be required to be removed with an air-cooled cooling solution. So it's important to understand that a direct chip cooling system is a hybrid system. It has an element of liquid cooling, but it still needs that element of air cooling. The benefit of this system is that it requires little modification to the servers, but it does require compatible hardware. So next we're looking at immersion cooling. So immersion cooling is where the servers are fully submerged in a dielectric fluid. The servers are fully liquid cooled, so there's no air cooling requirements. So the whole server, including all the ancillary components, all of the heat is transferred into the fluid. This supports the highest density racks. As we discussed previously, you can do it as a single phase where the fluid remains a liquid. And then you can also have it as a two-phase application where the fluid boils off and the vapor condenses and drops back into the bath. There's limitations and challenges associated with immersion cooling, one of them being the weight associated with these tanks, and that would be one of the limiting factors. And lastly, as I said, rear door heat exchangers. The rear door heat exchangers are not strictly liquid cooling. Your coolant is still piped into the data hall, but it's piped into a coil which sits on the front of your rack. The cold air is drawn into the back of the server, and the hot air or the heat is removed directly at the rack. So although this is not strictly a liquid cooled solution, it is a solution that is being looked at because of the increased rack density you can achieve with the rear door heat exchanger, and the fact that it's easy to retrofit into existing data centers. Fans are still needed, and that accounts for the increased energy consumption and the lower energy efficiency compared to a full liquid cooled system. All right, so let's look at what a typical system arrangement might look like, and this is just a hypothetical system arrangement. So what we can see here is in the blue would be a typical chilled water system. A chilled water loop, or what's, as ASHRAE defines it, is a facility water loop. So you have your heat rejection equipment in an external yard. That might be air-cooled chillers. Depending on the climate, it could be dry air coolers. If needed, they can be water-cooled chillers. So you have your heat rejection equipment, and then you may have a separate plant area or a plant space internally where you have AHUs or fan wall units that can account for your airside load. And then you have a piece of equipment called a coolant distribution unit, or a CDU. So your CDU hydraulically separates your facility water loop with your technology coolant system. So your technology coolant system is the system which comes into direct contact with your cold plates on your server. You could, theoretically, you could cool your servers directly with the chilled water system and have it as one common loop. The risk here is that you have a much larger system volume, which you're exposing your white space to in case of a leak. And you're increasing the volume of coolant that you may need. So the chemistry, the water chemistry in the technology cooling system is very specific, and it's at a very high standard. It's a high level of filtration is needed on that system. So if we separate the two systems, we can manage the water chemistry of the technology cooling loop that much better, that much closer. And again, as we mentioned, we can reduce the system volume. So this typical solution with some variations depending on the equipment and the arrangements, this is expected to be a very typical solution on a new build direct chip system. You'll have variations of this depending on the heat rejection equipment that you're using, depending if you're trying to install or retrofit to an existing system, but this would be a relatively typical approach. All right, the coolant distribution unit. So the coolant distribution unit is a critical piece of equipment within a liquid-cooled system. It's made up of so there's four connections to it. You have two connections for your facility water loop or your chilled water, your standard chilled water loop, and then you have two connections for your technology water loop. Within the CDU, you have a pump set which manages the flow control and the pressure control to your technology system. There's a heat exchanger within the CDU, and that allows, or that provides, that hydraulic separation between your facility water loop and your technology water loop. There are control valves and sensors which ensure temperature control and temperature management, especially dew point temperature. You don't want the technology water loop falling below the dew point temperature. Finally, you have filtration. So these CDUs come with typically 25 to 50 micron filters in them to filter out any contaminants or any debris that might be remaining or come about in the technology cooling system. So that's the role of the CDU, and that's becoming a very critical piece of equipment within these systems. All right, so in the next section, we'll talk about some of the challenges associated with implementing direct liquid cooled systems. But I'm sure a lot of us have seen in the media, seen on the news, and seen advertised by a lot of the equipment vendors, all of the advantages associated with the liquid cooled system. They're actively advertised. Better heat transfer capacity, you have increased densities, better energy efficiency and PUE. If you go with a liquid cooled system, you can generate heat for district heating applications. You get all these nice shiny brochures about how great liquid cooling is. This is a snip from NVIDIA and saying this platform boosts water efficiency by over 300 times. So there's a lot of good advertisement going on about all the advantages of liquid cooling. However, there's a number of challenges associated with implementing liquid cooled systems, and they're not spoken about as frequently. So I want to get into some of those and discuss and create a bit of an awareness about those challenges. So some of the challenges we'll discuss in more detail is material incompatibility, opposing liquid and air-cooled requirements, the direct coupling between the IT equipment and the liquid-cooled system, the complexity of preventing TCS or technology cooling system contamination, and slow system response to GPU power transients. So firstly, material incompatibility. So the selected materials of the technology cooling system has to be compatible with the selected fluid that's being used, whether that fluid is water, whether it's a glycol-based coolant, it could be a dielectric fluid, all the materials selected need to be compatible. In addition, galvanic or dissimilar metal corrosion is a risk. This occurs when dissimilar metals come into contact with each other while immersed in an electrolyte. So incompatible materials with large difference in electrochemical potentials causes metal degradation within the system. This creates debris which can clog the cold channels in the cold plates and abrade surfaces. Corrosion can increase the risk of leaks, and suspended debris wears component surfaces. This is a particular risk because some cold plates use aluminium as part of their construction, which has a high electrochemical potential difference between things like copper and brass, stainless steel. And then also using carbon steel on the piping system also creates that large electrochemical potential difference between the materials. So understanding the different materials within the system is key. Some of the wetted parts that are most prone to chemical incompatibility or corrosion include pump and internals and seals, the cold plate microchannels, manifold blocks and fittings, the heat exchanger interfaces, valves, strainers, and flow meters, as well as instrumentation, wetted parts. So some mitigation considerations. What can we do to mitigate this risk? I think an understanding of all the wetted materials in that system is key. This includes the IT equipment. Often we don't always have that information of what that IT equipment is, what the cold plates are made from, what are the manifolds made from. So this is a key part in understanding what those materials are and developing and maintaining a register of all wetted materials. Referencing specifications such as project specifications, OPC and ASHRAE recommendations. Tommaso referenced the TC 9.9 committee. They've got a lot of good documentation in terms of what materials should be used in these systems. Ensuring compatibility with the selected CCS fluids, and then very important, ensuring that the correct fluid chemistry is attained when you're getting that system flushed and started up, and then also ensuring that chemistry is maintained through the life cycle of that project, of that system. So next is the challenge of the opposing liquid and air cooling requirements. So cooling requirements for the air-cooled servers and the air-cooled loads, whether that be electrical rooms or switch rooms, those loads and those requirements differ from the liquid-cooled racks cooling requirements. So how is that managed? So there's some different options in terms of how the systems can be implemented. Either using the same low temperature chiller for both loads. You then forego any energy savings offered by the liquid cooled IT in terms of temperature optimization. Another option is to invest in separate high temperature chiller plants dedicated to the liquid loads, and then using an existing chiller for the air cooled IT loads. So what is the best cooling strategy, considering the IT equipment, cooling requirements, as well as the site environmental conditions? That's something that needs to be evaluated. The site environmental conditions will play a big impact in this capital equipment selection. It will determine how many hours of free cooling can be utilized, and will play a big impact in the efficiency of the system. What's key is understanding the IT equipment requirements. and that's gonna dictate the best cooling strategy, what the required server inlet temperatures are, and what the maximum allowable deviations are. We're seeing server inlet temperatures reduce and not always suitable for free cooling systems. So in my previous example, this was the typical solution, and that's because of the low temperatures that are being called for by the IT manufacturers. Using a high temperature chiller plant, this will allow the easier deployment of district heating solutions. And another consideration we need to think about is future proofing for changing requirements, changing rack and liquid types. Do we know what's coming? What are we designing for now? Are we designing for the next 5 to 10 years? Do we know what that IT equipment looks like in the next 5 to 10 years? And how do we manage that trade-off between the capital expenditure and system complexity, trying to keep things simple from an operation and maintenance point of view, and then also energy efficiency is always going to be a key driver. But at the end of the day, the IT equipment is what dictates what system and what system arrangement will be used. The next challenge is the concept of the direct coupling between the IT equipment and the cooling system. So in an air-cooled system, there's no physical connection between the cooling system and the servers. However, in a water-cooled system, it's directly physically connected to the servers. So what does that mean? What does that mean for us? How does that impact how we design and implement these systems? So additional space will be needed to be considered within the white space. We now have coolant piping, manifolds, flexible connections, drip trays, all serving the liquid cooled load within the white space. So that's all new elements coming into the white space, and space needs to be considered for that. With the densification of the racks, you have a higher capacity electrical infrastructure that's coming into the servers from a power distribution point of view. So coordination will be a challenge. Fitting these additional services into an already congested space will be a challenge. The racks are getting more dense, thus there's a concentration of services in a smaller area, and that's something to be considered. Also, with this concept of the direct coupling between your cooling system and your IT equipment, you have a challenge of managing the pressure drop variations across the technology coolant loop. In an air-cooled system, if you remove racks or remove servers, that has very little impact to the system, and you can manage that with adding blanking plates to manage your airflow. But within a liquid-cooled system, removing a rack will have a more significant impact. That will impact the pressure drop across the loop and could cause an imbalance, a hydraulic imbalance of that system. Also, if you have different servers and different racks or different server models within your racks, your hydraulic pressure profile across different server models, that differs, that changes. So how do you manage that? If you are removing racks or from your system, you have a risk of introducing dead legs into your system and stagnant coolant at unused branches. That can cause bacterial growth and contamination of your system. In a liquid-cooled system, the technology coolant system must be capable to meet the individual server cooling needs via the CDU pumps and controls. In an air-cooled system, so long as you have the air available in the area, in the space, the air-cooled servers manage their own airflow through the server. They generally have fans on them, and they pull their own air through and manage their own air. But on a liquid-cooled system, the CDU manages that coolant flow. The CDU manages the coolant flow through the TCS system, through the manifold, and then through the server. So it's a different approach. It's a different way of managing and controlling the system. With bringing your coolant piping into your white space, there's also a risk of leaks within the white space. So ensuring a robust leak detection system is in place is key. The coolants being used in the TCS, they'll require a specialized and separated drainage and containment system. We can't have these coolants leaking into the environment or leaking into the typical stormwater drainage system. So having a specialized drainage and containment system is key, in addition to that leak detection system. The next challenge we have is the challenge or the complexity of preventing contamination in your TCS. So contaminants can foul cold plates, leading to poor cooling performance and damage. This again, we're talking about the direct coupling of the liquid-cooled system. You're very much tied into the warranties of all this IT equipment. This IT equipment can be eye-wateringly expensive, and if, as a result of an improper coolant or coolant chemistry, that damages the cold plates, that damages and overheats the servers, is a massive repercussion for us as a result of that. So contamination, that can be organic or inorganic contamination, and can come from a number of potential sources during installation or during maintenance of the system, during testing of the system. So that's, like we spoke about earlier, incompatible materials within your system. Incompatible fluid sealants for threaded joints is a risk of contamination. Debris produced during the manufacture of the components. Microbial formation within the coolant at stagnation points. When we're testing these systems, load testing these systems, we're introducing load banks into the system. That can cause contamination of the system. When your IT equipment comes in, is that clean? Has that been used elsewhere before? Are there contaminants within the IT equipment, within the manifold, the rack manifolds for that? So there's many different sources of potential contamination. And I guess some mitigation, some ways to manage these risks is, like we mentioned previously, the wetted material schedule, ensuring all the materials are compatible. During the system arrangement, I spoke about limiting the size and the volume of the systems. If you have multiple smaller systems and one of them gets contaminated, it's less of an impact to the entire system. During fabrication and installation, prefabrication and assembly of components in clean environments will be key. Keeping that manufacturing process clean, ensuring contamination is not introduced during shipping and installation. But as well as you can do with that, you still need robust flushing strategies. You need to have a really good strategy to ensure that you're cleaning the system, you've got compatible additives, you're adding the correct additives and cleaners and biocides to the system to ensure there's no bacterial growth. When testing equipment like load banks are introduced, and when the IT equipment is introduced, we need to ensure that that does not introduce contaminants into the system. Time gaps between flushing, commissioning, and handover to operation. We need to ensure that the coolant is not stagnant during those periods and that there's continuous circulation and monitoring of the water quality during the whole process. And then finally, the other challenge that we need to deal with is the load profile of these GPUs. So during AI training, the power consumption of GPUs rise and fall simultaneously about 4 times per second. At these peaks, these GPUs may run at 150% more or more of their thermal design capacity. So that's an extract from a little paper there by the Uptime Institute and the erratic power profiles of AI clusters. So that shows us how quickly the load ramps up and down on these systems, and the fact that they're getting up to 150% or more of their thermal design power gives us an indication of what we're dealing with in terms of that load, in terms of that thermal load. So do we understand when we're designing a liquid-cooled system, do we understand the thermal load profile of the servers that we're designing for? This coolant system, can the system react quick enough on the onset of load? When we're going from 0 load to 150% load, can our system react quick enough? The best control strategy may not be the best control strategy for reliability may not be the best from a sustainability point of view. Are we going with a constant flow or constant differential pressure? We've seen both solutions being spoken about and in the initial designs that we've seen. So understanding what that load profile is a big part in how we design the control system. We have to trade off a performance risk versus the low load efficiency. Are larger temperature buffers or minimum turn down preference? Practically, when we're looking at the location of instrumentation within the system, that plays a big part in determining how effective the system is in responding to load, responding to higher temperatures. The control systems and the control strategies that we have need to be more multidisciplinary. They need to be integrated with the rack power profile, and that stages the cooling equipment on ahead of time before servers start overheating. There's a prediction, or if we know when the load is coming up, and we can start staging up the chillers and the cooling equipment ahead of time. And then from a testing and a simulating point of view, simulating the anticipated load, having those load banks in the system which can give you that instantaneous reaction, that 0 to 100% load. How does the system then react to that onset of load? And are we confident that that system reacts quick enough? All right, so I suppose just some final thoughts from my side. As rack densities increase and the need for better thermal management becomes more important, liquid cooling will become a more predominant cooling solution. I think it's with everything that we've said about liquid cooling, it's important to know that this will not be the only solution going forward. Air cooling is not going away. There are still going to be applications, and there is still going to be a need for air cooling when we're looking at less demanding and lower density workloads. The need for cloud storage, traditional business applications, that will continue to rise and grow and do not need liquid cooled servers. The correct implementation of a liquid cooled system is vitally important, and that includes all facets of the project, from design to fabrication and installation, the flushing and testing, and then the ongoing maintenance of the system. All of that is vitally important, and I think as in an industry, if we share information, if we arrange training such as this between these project phases and between these project teams, that's key to ensure the correct functionality of the system. And as well as once these systems are implemented, that we're improving on them going forward. Being aware of the challenges and how liquid cooled systems are implemented will support us in delivering fully operational, robust and efficient cooling systems. This will give us, sharing this information will give us the knowledge to ask the right questions, using good engineering practices and solutions to overcome any of these challenges. So I just want to end off by saying thank you very much for your time. Thank you for your attention. I hope you enjoyed today's talk. I hope you learned something and it was informative. And thanks again to Tommaso and the guys from ASHRAE for giving me the opportunity to present.
Thank you. Thank you, Jacques. Precious contribution, and thank you, Kirby, too. I open the discussion, so if someone have any question or doubts, curiosity, clarification, please do just activate your microphone. Paolo, yes, please.
Hello. Thank you for your presentation. It was absolutely essential. One point, because we are always dealing with, I think, misinformation on all sides, both users and developers and all of that, that consider that the liquid cooling or the hybrid system increases the total IT capacity of their buildings or their data center, despite the fact that all that heat needs to be dissipated in the environment, whether it's air or water or geothermal or whatever. So am I wrong that whatever we are discussing here is the primary circuit, so between the chips and the primary cooling system, but then all that temperature needs to have a chiller system or whatever to be dissipated? And is it changing somehow the proportion and the ratio between the IT power that you can get in a certain space, of course, because you're adding density, so in less space you can put more power, but in proportion, if your capacity to dissipate in the environment is 100, whatever it is fixed, that do you have any advantage in using the liquid cooling system as compared to the air cooled system within the system? So is it more efficient in terms of use of the power and use of the heat dissipation?
You're right, Paolo, and a lot of the time you are either limited by your on-site power availability or your heat rejection capacity. So what liquid cooling allows you to do then is instead of having a hall of, let's say, I don't know, 5 megawatt hall in 100 square meters, you now have 100 megawatt hall. I'm just using hypothetical values, a 5 megawatt hall in 10 square meters. So you very much have a much denser IT load or IT system, right? And you will have a more efficient system versus an air-cooled system. But it effectively allows you to run denser racks that support these higher density applications. So the advantage you get, you're using less physical space, but you're able to run these high density applications, these high density workloads. So I would say that's the advantage that you get, is that it's a different application in the workloads from an IT point of view that you're running. I don't know if that answers your question.
It answers 80% of it. So it means that you are building a smaller, the data center building. We are architects, so we have to fit everything within the box. So
Yeah.
the box would be smaller in terms of the size of the white rooms.
Yeah.
More or less the same size in terms of all the ancillary that is needed, like gensets and that all the electric part. That would not change because that is based on the total IT power you need. And then you have the other side, that is the rejection to the environment, whether it would be air or water or whatever. That is not changing basically.
Mm-hmm.
So the idea that developers have is that we increasing the density, you can build in the same building double or 3 times more the IT power, which then generates 2 times or 3 times more heat to reject, and sometimes that's a real limit. So yes, it's clear. Thank you.
Okay.
Can you hear me?
Yep.
Yes. Please
Hi.
just to introduce yourself briefly.
Absolutely. I'm Fabio Cassani, mechanical engineer from Arup. Thanks for the presentation, really interesting. I just wanted to ask or a bit of debate about the risk, the increase of risk of human error into the data hall related to the mechanical system, because now with the liquid cooling, we are going to have ops that manage in a more dynamic way. I mean, if you have a normal data hall, you have the CRAS, CRAS are basically there, they are statics, okay? But now you have to manage also the mechanical system, and in a dynamic way, because the population of the data hall varies. So have you experienced, or do you expect actually an increase of human error into managing this system? I don't know if it's a standard to use like a hydraulic coupling with a safety ball into the connection to avoid leakage, unexpected leakages, or someone just forgot to close the isolation valve. This kind of things is something that has been experienced. Are there safety systems that we can introduce to avoid these kind of things, or this kind of leakages or human error? What do you think?
Yeah, it's all things. That's a good question. Thanks, Fabio. It's all things that we need to consider when implementing these solutions, right? And what the risk is for these unintentional mistakes or challenges from the maintenance side, and fact, you know, I mean, I spoke about that direct coupling between the cooling system and the IT equipment, and that kind of plays into it, because there is going to be a much bigger impact when you're removing a rack out of operation, or adding a rack to the operation, and what the operations teams need to consider, because you're talking about leaks, agreed. There's a lot of quick connects in the market. Some of them have different ratings, some of them have different leakage allowances in them. But then it's also if you're putting, your maintenance teams need to be really switched on, because when you're introducing a rack into the system, you then have the risk of introducing air into your system, right? And what that does then to the efficiency of your system. Are you going to get cooling? So it's all of this. Whereas an air side, you can kind of add and remove racks. Just make sure you have the blanking plates in. It doesn't have a big influence. But you're spot on. The maintenance teams, and that's I suppose where we as an industry come in, and from a training point of view, from getting all the maintenance teams on board and aware of these risks and aware of how the system operates, what the impact is when you're changing that system, I think is a key fact. From a design point of view, there could be merit in having maybe a control valve shut off at some point to mitigate the amount of leak that may occur should a valve be left open, or should a leak occur. So that's all things that need to be considered as part of that design, and how strong the client's operations team might be.
Okay. Yeah.
Yeah.
Okay. Thank you very much.
Okay.
Thank you, Fabio, for your question. Someone else?
Hello?
Hi, I can hear you.
Hey. Yeah, wonderful. Hi, thanks. Just a quick question. I don't know if it's too specific.
Sorry. Please, Andrea, just introduce yourself.
Sure. My name is Andrea Vesconi. I'm a sales engineer from a company in Italy that develops valves, pumps, and other components, even for data centers and chiller and cooling application mainly. So I wanted to have your point of view, if you have any feedback about which are actually the best solutions from as pumps for for the cooling system. So which is, in your experience, the best approach and the best solution for the time being for this kind of project and applications?
In terms of the pumps,
as pump technology, principle or working principle. I don't know if it's too specific or something that you have some feedback about.
yeah, it's going to be a relatively low, I don't know how specific I'll get in the answer, but it's going to be a relatively low pressure. I think we were talking about 4 to 6 bar system maximum. So, and there is differing opinion on whether it should be a constant flow system or a constant pressure system. I don't know if that's something that's been across the industry, something that's standardized and been decided on. I think we're yet to see in these larger systems what the best approach is. The centrifugal pumps, they're going to be built into the CDUs. like I explained there. So they're going to be part of the CDU, and that CDU is going to be a manufactured piece of equipment with the pump on it and the integrated controls within that CDU. And then in terms of the components, like I mentioned, it's just making sure that the components and all the wet materials on that pump is compatible with your working fluid and with all the other components within that system. So especially your seals and your gaskets, making sure that they're compatible with your coolant. That's probably going to be a PG25 coolant, a glycol-based coolant. And then it's probably just down to the efficiencies that you're getting at those operational points. Especially that's going to be one of the big power draws for the system, is your CDUs and your circulating pumps. So I believe the efficiency of those pumps is going to be something that's going to be a key factor, because as fans have been in an air-cooled system, it's now going to be your pumping system and your pumps that are going to be utilizing a lot of your energy in that system. So the efficiency is probably a key part of it.
Right. Thank you.
Okay, no problem.
Hello. Can you hear me? I have a question.
Hi, Alessio. Yeah.
Yes.
I'm Alessio from ARUP. I'm more in the energy sustainability department here in Milan. Talking about efficiency, I was interested on the topic related to driving the PUE down with the liquid cooling. Maybe can you expand a bit the impact of liquid cooling on respect to usual air approach in the data hall? I mean, what are the main pros, advantages that you've
Yeah,
seen?
I think, Alessio, I think the key part of it is that, we're using fluid, we're using a liquid instead of air to transfer the heat between the servers and the heat rejection equipment. So the fact that we're using a fluid, and as I mentioned in the presentation, water can be 3 times more efficient, or has 3 times more heat capacity than air, right? So for every volume of water can carry 3 times more heat than what air can. So you're having to put less volume of fluid through your system to carry away the same amount of heat, right? So you're moving less fluid.
Okay, and also it's
in a
I mean, you don't. It's extremely localized.
Yeah, exactly. And there's probably a bit more efficiency on that control in a liquid cooled system. You're directing that fluid directly to the heat source, whereas there's probably more inefficiencies when it comes to air, especially with your air containment systems. There's a lot of inefficiencies which creep in air containment, right? Whereas with the fluid, you're directing that fluid directly to the chip, directly to the server, and removing that heat at source. So you're removing more heat for less volume of fluid that you need, and that's probably where the big efficiencies come in if it's done correctly.
Okay.
But again, it all has to be looked at holistically. Right. I've not done the direct comparisons myself, but a liquid cooled system doesn't necessarily mean you're going to get a better PUE, you're going to get a better efficiency, because a lot of it depends on the temperatures you're running at, right? If you're designing a liquid cooled system with a 12-degree supply temperature versus an air cooled system with a 30-degree supply temperature, you know what I mean? You're probably not going to be designing a more efficient solution.
Yeah.
So that's why I said just going to a liquid cooled system doesn't guarantee you in a more efficient solution, but it can do. And a lot of it is dependent on the temperatures. And there was a stage where everyone was very happy because the temperatures were looking quite high we're looking at kind of 30, 35 degrees supply temperatures to the racks. But now this has dropped down 10 degrees. The designs we're looking at are between 20, 25 degrees supply temperature. And then if you're talking a 3-degree approach, you're talking, I don't know, anywhere from 18 to 22 degree supply chilled water temperature. And then in somewhere like Milan, you have not so much free cooling available at those temperatures. So you're talking about a lot of mechanical refrigeration then. And what that then does to your PUE versus, like I said, an air-cooled system at 30, 35 degrees supply temperature. So it has to be looked at holistically in terms of the whole design and the operating conditions. But yes, it has the potential to be a much more efficient solution because of that heat capacity of your liquid.
Okay, many thanks for the comment and your presence.
Okay. You're on mute there, Tommaso, if you're talking. I don't know if there's any other questions.
Sorry.
No.
Just let me add one thing about removing the CRAS. You remove all the fan power that you need for the cooling of the racks, no? And with the high density server GPUs, you will need a lot of airflows, a big amount of airflows that first of all create problem from the space requirement, and then the handling of the air volume that increase exponentially the power consumption of the fan. So that is the biggest difference if you stay with the same amount of outdoor condition, water temperature condition. That is the great difference. Pumping is much less costly.
Yep, exactly.
Some other question?
Okay. This is Mauro from 𝗖𝗵 in Italy. I have a question for Jacques. Okay, hey Jacques. By traveling around a lot of data center influencer and consult engineer, my question is, what are nowadays the situation about who certified the data center or the liquid cooling systems? Because talking with them, a lot of consultants, a lot of solution around the world. Okay, especially in the UK, when I'm also talking with Kirby and Ireland. What is nowadays when you talk about the who certify? Because the main question is we have the knowledge, we have the technicality, we know about air, we know about liquid, but when the solutions come, what is the situation about when to certify these projects? Who certify? Because it seems to be an early stage for everybody.
I'm not 100% sure what you mean by certifying it. Do you mean kind of who guarantees that, who validates it?
Yeah. Yeah, correct.
Yeah, and I think a lot of it is going to be more dependent on the IT equipment manufacturer. Typically in an air-cooled design and an air-cooled solution, you've got the ASHRAE classifications, right? So you've got the ASHRAE design recommendations that you've got to fall within, and the server manufacturers will say you need to be within this range. Whereas my understanding on a water-cooled system, we're much more reliant on the IT equipment manufacturers to specify the temperatures required, the flow rates required, and validate the various equipment feeding that IT equipment. So the likes of your CDUs. So I don't know who ultimately signs off or who ultimately certifies that system, but certainly there's going to be a lot more involvement needed from the IT equipment manufacturer, right? So there's going to have to be buy-in and review done with the IT equipment vendors to say that if you implement this system and it operates correctly, you're within your warranty parameters for the IT equipment. I think that's going to become a lot more important. It probably is already important, but it's going to become a lot more important because of the fact that, like I said, that direct coupling between your cooling system and your IT equipment. Your IT equipment in a liquid cooled situation is a lot more dependent on your coolant system for cooling or providing that cooling than what it is on an air cooled system because of that direct coupling. So there's going to have to be a lot more integration and a lot more discussion with the IT equipment manufacturers to make sure that what we're implementing, what we're building is within their requirements. I hope that kind of answers your question.
Okay, now it's clear.
Okay, thank you, Nicola, for your question. Any other question?
Just to know if the presentation will be made available. Your slides.
Yeah. Yes, will be available, and also the recording of the webinar will be available. We will share in the LinkedIn and YouTube channel.
Okay, thank you.
Thank you. Other question? Doubts? Curiosity? I have a question, Jacques.
Yeah.
About the TCS, the technical cooling system. No, each of the branches that go to the server, let's suppose a direct to chip system. So each of it will have some regulation valves, no?
Yeah.
Usually these valves are regulated by the SCADA or by the server itself, by the rack itself.
The only thing I've seen at the moment in the designs we're looking at, and the most common seems to be a pressure-independent flow limiting valve. That's if you're using a constant differential pressure. That's if you're using a constant volume system, right? At each of the branches, there's a pressure-independent flow limiting valve. So it makes sure that only a certain amount of flow gets through the branch, right? And that's set. So whatever the pressure variation is upstream, you're getting your required flow to your branch and to your rack. So it's a pressure-independent flow limiting valve. Seems to be the valve that's being specified for those branches, and that would regulate the flow down to the rack.
But there is a regulation, or the flow will be constant through the rack to avoid any problem of control gap, delay.
I would say it will be a constant flow through the rack. That's the conservative approach, right? That's the conservative approach, that you'd have a constant flow going through your rack, so that whatever happens to your load, you always have cooling availability. but again, you then lose energy efficiency, right? Because you're constantly circulating. So there's, you know what I mean? That's what we were talking about, the trade-off between performance and performance risk versus efficiency.
Yeah. In the moment I saw like this, no control and just constant flow inside the rack. Okay, thank you. Any other questions? Okay. I think that we can close the webinar. Thank you. We are just in perfect time. Thank you again, Jacques, for a very precious presentation. Thank you to Kirby, and thank you to all the participants, and thank you also to the ASHRAE group that organized this event. And nothing, we will share the presentation, the recording, and we will keep any update for our next event. If someone else want to contact direct Jacques, if it's needed, just let me know, and I will provide his contact, or I think that you can contact him on LinkedIn.
Yeah.
And thank you to all.
Thanks
Thank
all.
you. Bye.
Grazie a tutti.
Cheers.
Bye bye.
Bye. Ciao.
Grazie.
Bye bye.
Bye bye.
Thank you, bye bye.
Ouais, mais qui c'est? Je suis pas loin.